Thank you. Thank you also to Daniel for this nice presentation. And as you understood, this is coming soon. So I'm going now to have a short overview of the kind of algorithm we want to implement for our primary objectives. I will have a short chapter about generalities, and I will switch to bright limb and occultation. Of course, in this limited time, it is not easy to speak about everything. I want to come back on the way we are planning to represent ozone profiles, because it's, let's say, a little bit innovative with respect to gridding procedure. And basically, we would like to develop the ozone profile over a basis of orthogonal function. And one of the standard way to do that is to have a big ensemble of ozone profile, like on the left side, and to compute the covariance matrix, to diagonalize it, and to use in a principal component analysis the eigenfunctions produced by this process. It is also called empirical orthogonal function. And this is not really new. If you look at the book of Rogers, you see that it is recommended actually to use this kind of representation, because you can get more than 99% of the variance described by this, this analysis as soon as you have, let's say, more than 10 functions components. So we need a big training set, which is taken from climatologies. We extend the domain to twice the median value, and we will generate an homogeneous and large data set inside these boundaries. When we play with principal components to represent an ozone profile, at the same time you define your resolution, and your resolution will be actually dependent on the number of components you use, from 1, 3, 10, and of course, as one you have as many, let's say, components as layers in your atmosphere, you have a delta function. So this is already an old slide where I was comparing some occultation experiments, ACE, GOMOS, with the limb measurements, schema key, ohms. And you see that today, using 20 principal components for a signal-to-noise ratio of 500 would lead us to vertical resolution of about 3.5 kilometers in the mid-range of other instruments. So you could ask, why don't you increase the number of principal components to increase your vertical resolution? And by an example, I will re-explain with this slide that you may have a profile with small details that you convolve with a large sampling, a broad sampling instrument, and the convolution of it has still the trace of this, so it can resolve actually these fine details. But if you add any noise, you see that this is disappearing, so there is a clear relationship between your resolution and the signal-to-noise ratio. You have to adapt your resolution actually to the signal-to-noise ratio we will have. So I jump to the limb, and for the limb we need, of course, a radiative transfer model. From already a long time ago, we selected to go to, the requirements are, we need a fast model, vectorial, spherical, with refraction at, let's say, 1% accuracy, because it's a complex problem. And Monte Carlo methods were, in the past, considered as reference method, because microphysical law were implemented, but too slow and only for reference. But IGEOS France developed a SmartG that we are using, and the main change consists of the use of graphical processing units capable of shooting millions of photons per second. Unfortunately, we are not allowed in the near real-time processing to have GPU hardware in the processing chain. For a technical reason I don't want to explain. And so we need some lookup table approach as a proxy to the results of our Monte Carlo simulation of the radiative transfer. So basically, a minimum set of wavelengths to retrieve ozone, I say the minimum, would consist of UV information for the upper stratosphere and visible information for the lower part. We have three favorite wavelengths you probably already know in the UV, and 3 wavelengths in the Chapuis band for the lower stratosphere. So we will use multiplets, doublets, and triplets for different normalization. This is here an example of the radiance that you have in the UV without ozone and with ozone. Of course, the transition is large. And finally, we develop doublets, which are ratios of wavelength in the UV, but also in the visible, where you use some geometrical normalization, a classical approach that was implemented a long time ago, in such a way that we produce a signal with ozone that is clearly different than without ozone, and actually the information is here. Why do we do that? Because basically from the beginning, ALTIUS doesn't have an absolute calibration of the radiance. So we are forced, as in many other instruments, to renormalize the radiance also in altitude, to factorize the detector sensitivity and other factors. And also we use a spectral normalization by the doublet and triplets to have some differential effects. So there are basically 2 kinds of renormalizations in the processing. Then the problem is in general, to match the coefficient of the principal components, including and also geometrical parameters, sun angles, also some information about albedo and aerosol, and to produce this doublet, triplet with the forward model. And this is why we have this, let's say, some lookup table approach. This was the past, and now this is a quite stable situation where our state vector, the input of the forward model, consists of up to 20 principal components, 5 for aerosols, 5 for air, an aerosol effective radius, and a particle size distribution width, plus 1 effective albedo and the 2 solar angles. So 35 parameters, and we compute the Stokes components at, let's say, a sampling of 2 kilometers over 0 to 60 kilometer range. And so our lookup table will consist of this mapping between the state vector, the radiance vector, and this is done by a neural network at a 1% accuracy. So for the retrieval, there are many of algorithms possible, but you see that signal-to-noise ratio and number of principal components are related. If it is a very low signal-to-noise ratio, you see underdetermination, and when you increase signal-to-noise ratio, you are allowed to use more principal components, and you see the error bar decreasing until, of course, an excellent retrieval with 13 principal components. Well, one step is finally, we don't know in advance how many principal components you are going to use. So we have an algorithm that is looking at the chi-square distribution of the merit function, and you see that when you increase the number of principal components, you decrease your chi-square until you reach the standard value of 1, where which should be optimal, because you switch from underdetermination to a regime where you have roughly noise amplification, and this is the optimal value that is chosen. Well, I don't speak here about the role of aerosols. They may interfere, but we are in an approach, a step-by-step approach, where for every ozone retrieval, aerosol is fixed, and then it is foreseen to update the aerosol value to have a consolidation of ozone. So basically, the ALTIUS ozone retrieval scheme consists of 3 loops. The most internal one is the classical let's say, a comparison between prediction and observation, which is nonlinear but iterated by a standard algorithm. Then, for a given number of principal components, then once it is converged, we increase the number of principal components until we reach this criterion of chi-square equal 1. So these two loops consist of the components of the near real-time algorithm. And when we will consolidate it, we will introduce, we will update aerosol and albedo in order to improve the ozone results. So to be sure that we had a correct approach, we also implemented direct inversion. So no principal components, no lookup table, only Monte Carlo as the forward model, and this was done by Antonin Berthelot, and I invite you to have a look at his poster this afternoon, I guess. And we have a good correspondence, and it was just to check that we had the control on the results. Of course, when you use the direct method with SmartG, it's maybe 50 to 100 times slower and not acceptable for near real time. It is just a control. So we have various tests where we can compare the results between the direct method and the nominal L2P method with the PCS. And we also have Monte Carlo simulation to control that our error budget propagation is correctly done. One of the problems is, of course, that when we really simulate realistic scenes at an extremely high resolution, spectrally and spatially, it takes a lot of time, and also the instrument simulator is, let's say, comprehensive. It can handle whole kind of processing at level 1, and so it takes a lot of time. So finally, when we want to test our error budget today, we have to be cautious with what we call Monte Carlo simulation of error budget. It is a restricted Monte Carlo approach due to computing time. So this was the LIMP. We also have stellar, planetary, lunar, and solar occultations. Antonin will also present the way we are planning to handle this well-known scintillation problem that we know since GOMOS, and he will show how we are going to mitigate this residual modulation due to scintillation. You see that even in stellar occultation, we have some resolution between 2 and 4 kilometers. Even with stars, the problem is that with stars, they are fainter, and so we need to integrate more. So to integrate more means a loss of vertical resolution. We are also thinking to lunar occultation, of course, with the hope that the solar algorithm could be applied independently of the lunar albedo in an easy way, and we have a preliminary test performed by Philippe Demoulin. He has a poster. Please go and discuss that with him. And we have already thank you. We have already good confidence that lunar mode will be doable and extremely useful for the repartition of our geolocations. Well, this is not yet done, but we have time. We would like to do self-validation, which means after a sunset, where let's say the spacecraft is in inertial mode, we would like to switch to the LIMP mode and to observe the twilight light. So the sun will be beyond the horizon, and we will be able to sound the same air volume, but with two different techniques: occultation with self-calibration and LIMP scattering, and so of course to intercompare the results. So, but probably we will have to for that to develop a dedicated algorithm, because their single scattering is dominant. Forward scattering of the phase function is critical, and retracing should be very accurate. Okay. So the summary. For all modes, we are using this representation of ozone profile with orthogonal functions coming from PC analysis. I will not read all particular aspects I just mentioned, but overall the Ozone L2P, the operational processor, is certainly under control, is almost ready for an optimization phase. The consolidation of the performances will, of course, depend on the error budget coming from the L1, and they will have, of course, an impact, not only their absolute value, but the knowledge of the L1 error. So thank you for your attention.